Hi everyone, I'm Anna, and this is my Physics 2 Lab 2 lines of charge. In this lab, I build on Lab 1 by improving the physical model of charge tape using a distributed line of charge approach. So the purpose of Lab 2 is to improve the point charge model we used in our previous lab. Instead of treating the tape as a single point charge, we model it as a line of evenly distributed charge. And then using this model, we numerically calculate electric fields and forces, determine the charge required for levitation, and compare the results to the point charge estimate from Lab 1. So several things stay the same from Lab 1, including the tape length, tape mass, and floating distance. What changes is the model. The point charge approximation is replaced with a line charge model, and instead of a single force calculation, we now compute the sum of many forces using a numerical glow script model. The procedure is entirely computational. First, I use the measured values from Lab 1 as inputs. Each tape is split into 100 small charge elements, and then for each element on the bottom tape, I calculate the electric force or the electric field due to all elements on the top tape. And then I compute the force using F equals QE, the sum of forces over the tape, and compare the electric force to gravity. This lab uses Coulomb's law to calculate electric fields superposition to combine contributions from many charges, and Newton's second law to apply force balance. Distributed charge modeling and numerical summation allow us to represent the tape more realistically than just the regular point charge approximation. So the system in this lab is the bottom tape. Since the bottom tape is free to move and when it levitates, the net force on it is 0. The surroundings include the top tape, which is held by hand, the earth providing gravity, and the electric field. For levitation, the electric force on the bottom tape must be upward and equal in magnitude to gravity. So the tape is a long object, not a point, and its charge is spread along its length. So because closer charges produce stronger forces, concentrating all charge at one location can misrepresent the physics. So modeling the tape as a line of charge captures geometry, distance variation, and just a more realistic force distribution along the tape. So the measurements we used were all came directly from Lab 1. So the tape length from before is the same. It's 0.1778 meters. The tape mass that we calculated before was 0.0001778 kilograms. And then the tape separation is 0.0279 meters. And then the tape is split into 100 charge elements. But no new measurements were required for this lab. So in the glow script model, each tape is represented as a line of small spheres, where each corresponds to a charge element. So the green arrows represent the electric field vectors at different points along the bottom tape. And then the white arrow shows the net electric force acting on the bottom tape. The yellow arrow represents the gravitational force acting downward on the tape. And then, the electric field and forces were calculated numerically from using superposition. So the arrows are scaled for visibility so they can show direction, but not true magnitude. The electric field function calculates the field from a single charge element using Coulomb's law in vector form. The direction comes from the relative position vector, and the magnitude follows the inverse square relationship. And then these individual fields are later summed to find the total electric field at the bottom tape segment. And then each tape is split into 100 charge elements with both charge and mass evenly distributed. And then this replaces the point charge assumption from Lab 1 and allows the tape's geometry to directly affect the force calculation. So 2 identical tapes were created in the model. The top tape is given the opposite charge sign, so the tape's attract. The bottom tape is the system and is pulled upward, matching the physical setup of the experiment. And then for each charge element on the bottom tape, the electric field is calculated by summing contributions from all elements on the top tape. The force on each element is found using F equals QE, and then these forces are summed to give the net electric force acting on the bottom tape. And then using the point charge model from Lab 1, the estimated charge magnitude was approximately 2.24 times 10 to the negative 8 coulombs. And then using the line charge model from Lab 2, the estimated charge magnitude was approximately 2.38 times 10 to the negative 8 coulombs. The values are close, but the line charge model predicts a slightly larger charge because spreading the charge along the tape reduces the force per unit charge. So assumptions include ignoring air resistance, assuming uniform charge distribution, and assuming both tapes carry equal charge. These estimates differ because the point charge model concentrates all charge at one location, slightly overestimating the electric force. The line charge model spreads the charge along the tape, making it more realistic for a macroscopic object. The line charge value is more likely closer to the real charge because it better represents how charge is physically distributed. So in conclusion, Lab 2 shows how improving a model changes quantitative results and explains the limitations of the point charge approximation used in our previous Lab 1. Thank you.